we ended up last time. Do you have any questions? I feel like you should have more questions. Unless you're confident you're going to end up with an A+, you should always have at least a question that will bother you. Wouldn't let you go to bed at night. Yeah. Can you check your phone?
Sure.
Any questions about phase contrast? Dark field, martial arts, analogy? Okay.
That filter A times exponential I alpha.
Yes.
So A is the attenuation.
Yes.
But you said that the practical value is 2 or 3.
1 over 2 or 3. Sorry. 1 over 2 or 3. You're right. So this should be 2 power minus 1. So this is an attenuation. You're right. Yep, thank you. Other questions?
Why don't you put A up in the exponent instead of using?
Here?
Yeah.
This is a little small. Well, the filter does two things. It attenuates according to A, and the phase shifts according to alpha. So we need one in the amplitude, one in the phase. It has to be there in the amplitude, unless I misunderstood your question.
Oh, because usually when you say you have like an exponential decay of the field as it passes through something, right? So
Oh, yeah. Oh, I see what you mean. So you mean Lambert-Beer's law or something?
Right.
Yeah, well, what happens is this. So imagine you have a plane wave, and basically your filter, if we zoom in, it's a little piece of metal that could be, actually I made up a homework a few years ago. So this could be like a thickness L. Okay, and usually this has an attenuation, let's not call it alpha, let's call it beta. So according to the Lambert-Beer's law, how many of you know Lambert? Everybody knows beer, but same spelling. Okay, Lambert-Beer's law. Well, it tells you that the attenuation, so after thickness L, the intensity that is left unattenuated is what you put in I naught e to the minus beta thickness L. So you're right. In an absorbing medium, your intensity will decay exponentially. True, but I don't care about these details. What I'm going to say is that at the end of this whole exponential actually will be 1 over 4 to 9. It depends on the objectives. Okay? So the material absorbs exponentially, but we don't care about those details. We say I put in I naught, I get back at the output I naught over 5. Yeah? All right. I feel like we are communicating now. Other questions? Same law applies to scattering, by the way. Next chapter will be on scattering. That if you send a plane wave through a scattering medium, like through a cloud or through a tissue, the plane wave that goes through unscattered will continuously decay in power, exactly like this exponentially, except now this attenuation factor is called the scattering coefficient, not absorption coefficient. So beta is absorption coefficient. Do you know what beta is related to? What makes the material attenuate? Would a piece of metal absorb more than that piece of glass? The window? Yes. What's the difference?
in terms of
material property, like
material properties.
Yeah, fundamental. What's the difference between a piece of metal and a piece of glass? Conductivity. Exactly, conductivity. So beta has sigma in it. Conductivity. The bigger the conductivity, the bigger the absorption. And why do you think that is? That's the difference between a good conductor and a good dielectric. Low conductivity, like that piece of glass. High transparency, no dissipation. Why is it that high conductivity gives us high attenuation? That's the reason, by the way, your X-rays show your bones and not your soft tissues. We talked about that, right? Because in X-ray you get the projection of an attenuation map, basically. And the attenuation in soft tissues is not very high. So you get very low contrast. This beta is very small. That's why you need to go to MRI. So, okay, so fundamentally, why is the attenuation high for high conductivity? So I want you to think at the microscopic level. Why do you think? First of all, what happens to the light that is absorbed? That energy, where is that going, finally? Heat. As usual. That's energy lost, eventually gets into heat, right? Put a laser on your tissue. Eventually, you are going to burn the tissue. Right? You put a laser on a piece of metal. That's why the lasers can be used for cutting, right? Metal and other things. Okay, so what happens at the microscopic level? How is that heat generated? Electrons. Basically, it's the same thing as in an electrical circuit, right? It's the resistor that gives you the heat, right? Not so much the coil and the capacitor. They are acting as a storing. The equivalent of a capacitor or an inductance is the refractive index. So you have a transparent medium like that. You can kind of store energy in the glass, but the light keeps propagating, so you don't lose it. You can recover it, right? So what happens is that basically, as the electric field hits the material, the electric charge is following that electric field. Now, in a high conductivity material, the charge is loose. For an ideal conductor, the charge is free, which means it's free to follow that electric field that I put in. So this is an electric field that has a certain magnitude, and it oscillates at the femtosecond scale for this wavelength, right? Very, very fast. So now, if you accelerate these charges and they start to move around, eventually they start having, how do they lose their energy? They collide. Mainly with the lattice. So basically, through collisions, the energy is dissipated, and eventually you get heat out. When you have a good dielectric, the charge is bound to the nucleus. The electrons are very tight to the nucleus. You disturb them a little bit, but you don't really break them free, so to allow them to bounce around and lose their energy. So they're very tight. It's basically not losing any energy. Okay? So that's why we can see through that glass. Yeah.
And that's called Joule heating? That's called Joule heating?
Joule heating?
Yeah, an electrical event.
I guess, I don't know. You can call it just heating. But Joule is a good unit for people call it Joule heating, I don't know.
I remember
in antennas, or I don't know.
Yeah, the dot product of the electric field and a magnetic field are crossing over, non-zero, then you have heating. And then E cross B is the pointing vector.
Right.
So any component of the B field on the E field is heating.
Okay, yeah, call that Joule heating. I don't know exactly. Okay. But must be a good word for it. Okay. That's why having a piece of metal does both the jobs, because there is a refractive index, there is a thickness, and the refractive index for that metal that gives you a phase shift. And also it attenuates very hard. As you know, metal is really very high absorbent, right? Although it could be made transparent, as you know, right? So all these, like gold, if you pull it in very thin sheets, you start to see through it, except that foil has to be a few nanometers, right? Oh, a famous example, in the Red Square in Moscow, they covered all those churches, the famous churches, with gold. Okay, so it's like square miles of roofs covered in gold. The total amount of gold was actually a few kilograms. I think 16 or something. So you can make it very thin, make it look rich with actually a very small amount of money. Okay, enough about stories. So we're moving on. At the end of the day, the Nobel Prize in Physics went for this. From going to a transparent cell, where you cannot figure out what's inside, to something that really shows you the internal structures of the cell. And best of all, without kind of disturbing the cell too much, without adding anything from the outside. This is what we call intrinsic contrast, as opposed to exogenous. Okay, so as I said, every lab, everywhere has a phase contrast. If you grow cells, you have to have a phase contrast by your incubator just to check on them quickly. Okay. Now we're moving to holography, which is another Nobel Prize winning idea. Did you know that holography is subject to the Nobel Prize in physics? Yeah? Holography is one of these funny subjects that I think everybody knows about, like our grandmas heard of holography. My favorite rock band in Romania was called Holograph. I don't think they had a deep understanding of what that meant, but what people do, they're associated with the 3D imaging, isn't it? When you think about holography, you immediately think about 3D. Well, that created a lot of confusion, in my opinion. And the confusion came from the fact that people manage, using phase information, people manage to make objects look 3D. But they look 3D to the eye, meaning if you covered one eye, that 3D feeling disappeared. So in the same way, you get a depth perception just because you have two eyes. But that's not really 3D imaging in the sense of MRI, where you have sectioning through a 3D object, right? And to this day, actually, there's a lot of confusion in the publication in the optics field, like assuming that holography immediately means tomography, and that's wrong. We're going to make this clear distinction as we go. Okay? So the difference is that you can actually, if you have the phase and amplitude information of a field at a certain plane, we just learned previously that I can propagate it numerically anywhere I want, right? With the Fresnel kernel. I just do that convolution, I can figure it out everywhere, right? But that is propagating the field in 3 dimensions, not imaging an object in 3 dimensions. Very different thing. In other words, if you propagate the field with the Fresnel kernel through the field passing through an object like a cell, you are not going to get the 3-dimensional structure of the cell just because you are able to propagate numerically the field. You have to do a transformation from the field in 3D to the object in 3D, which is called an inverse problem, which is a scattering problem that we're going to study next. Okay? So keep this in mind. 3D, what appears to the eye as 3D, probably you looked at the hologram, so you see this kind of light floating in thin air like that. So it's interesting, it's entertaining, but it's not a 3D image of an object in the sense of a tomogram. For that, we need to put a lot more effort, actually, to do. And the 3D effect will disappear if you cover one eye. So that the brain is mixing the two, pretty much like when you watch Avatar with the goggles. It's the same kind of effect, that the brain is mixing two channels slightly offset in angle. So it's giving you two slightly shifted views of the same object. That's what makes us feel that 3D kind of depth information, which is useful, don't get me wrong, but it's only two views of that object, this and that. When you talk about tomography of an object, as we will see in scattering, it's a little bit more complicated. Okay, but enough about the bad things about this confusion with holography. Holography is a great technique. The funny history of it is that Gabor, the inventor of this technique, Gabor was a Hungarian scientist, actually, an electrical engineer. He wanted to do something else completely. He wanted to fix electron micrographs. So he realized that the electron microscope, I think I mentioned to you in the very beginning, the wavelength of the electrons, the Broglie wavelength, is very, very tiny. It should be, if you operated that at diffraction limit, you should be able to see atoms and subatomic structures with no problems. The reason we cannot do that is because of aberrations. We talked about the lenses are now coils, and it's a little bit of a mess. So Gabriel thought, how about if somehow I manage to kind of extract that aberration by optically reading the aberrated electromicrograph and then fixing it with optics, where I can afford all these lenses and we have all these luxury and tools in optics to do diffraction limited imaging. Well, long story short, that didn't go anywhere. Although his first paper did contain some kind of a micrograph. So his first paper was, I think, this one, 1948. But really, holography took a path of its own, and it's been associated ever since, really, with optics. Okay? So the idea is that the name itself, what holography is about, is to add phase information to your imaging. It's really this connected to what we just did last time with the Fresnel propagation, for example. If you have the complex field, amplitude and phase somewhere, you are able to actually reconstruct the field anywhere along the z-axis, which is kind of a powerful idea, right? But for that, it's very important that you have the phase information. You just have the if you just have the amplitude, meaning if I, for example, I take a camera picture of this screen, and then you ask me to propagate it, let's say, back here, I won't be able to, just because once you took a picture, the phase is gone. So holography deals with this idea that we need to use the whole information about the field, amplitude and phase. So amplitude is easy. You just take a snapshot. The intensity is the square of the amplitude. The hard part is the phase. Okay? So in his original setup, the way he did it was, so remember, this is prior to lasers. It's another interesting thing. So they had to struggle with sources like this, make them coherent. When we talk about phases, we need to have the field coherent. They had to filter the sources, both spatially and temporally. And here's how it works. So imagine you have a thin object like a transparency. Yeah? And then you collimate the light. Imagine this is a point source like a lamp, but as small as possible. You make a plane wave, approximately. You illuminate the object like this. And then you have a film. No digital cameras, 1940s. Okay? You have a piece of glass here that is photosensitive. Okay? Grandma style. So what this film is going to get is information about both amplitude and phase from the object here. Okay? You'll get a messy looking thing. It's not going to look like your image anymore, right here, like your object. It's going to look like a complicated interferogram, right? So it's an out of focus version of this object where you have a lot of interference, rings. But that's where the meat of the problem is, that in that interference, you actually have the phase information. So that's step one. That is writing the hologram. So now you have actually a piece of glass that contains the phase and amplitude information from the object. That distance from the object is actually contained, so this distance, let's say L, is contained in how big these rings are and so on. So that scaling is actually contained in that piece of glass. So basically, you could take this away with you and put it in your pocket. And then, in order to see the hologram, you have to go to step 2, which is reading the hologram. So you write it first on a physical thing, and then you take it, and here's how the reading goes. You take the film, the piece of glass that has the hologram on it, and then you illuminate it with the exact same beam. You place this here, you take your same collimated beam, the light will diffract. This is essentially a complicated diffraction grating. It's not just one sinusoid, it's a bunch of sinusoids according to what hit that film when we recorded the hologram. So all the diffracted light from the object, right? This generated here a very complicated diffraction pattern. or grating. Now, when I illuminate this diffraction happens again, so I'm going to have a wave that propagates this way, another wave that propagates backwards, right? But if you look at the equation, something interesting happens. So first of all, the transmission, so the function associated with the hologram, what I recorded, is actually proportional. There's a background. Actually, back when I was an undergrad, I was reading about this. I had an old professor who actually grew up with this, with the plates, spectroscopy, old school in the 60s. So I studied these at some point. I forgot most of it, but I studied how the response of these physical pieces of glass that nobody's using now, I don't think. Long story short, you have a background, the response of the glass. So the idea is, if I have that photosensitive film, like your old camera, did you guys ever touch the film cameras? You did. How many? Can you raise your hand? Everybody? Okay, that's nice. So you know what it looks like. It's a nice cassette. Okay. So that thing has a response, right? That has a dark, if you want dark, like dark current equivalent response, right? No light, but still some background. That's this. But then the interesting thing is, the more power you put, the more intensity, the higher the transmission. Okay? So first it becomes dark, or it becomes negative, then you develop it and becomes okay, so where you have higher intensity, it looks whiter. I think that's the way in X-rays too, right? Yeah, the bone looks white, right? That's okay. Okay, so then now this is my transmission function. So notice the interesting thing. The transmission function of this object is proportional to the intensity. It is like a detector. It's not sensitive to phase, but this intensity actually had phase information from the object because it's a little bit away from the object. So now I take that transmission function, and what I'm doing with it is I put my plane wave U0. So right after this film, what I get out is actually U0 multiplied by the transmission function. Yeah? So if you do the calculation here, what you get is U0 times, and now I do the, wait, this is wrong, huh? No, it's not wrong. So what is the intensity? I think that's what's missing here. The intensity is the magnitude square of the total field that came from the object. So from the object, I have my plane wave, which I call U0, and I have my scattered wave, which I call U1, exactly the way we decompose them in the phase contrast. You remember that? So U1 is the scattered part, if you want, or the high frequency component. So the intensity that goes into the transmission function is the magnitude square of that. So it's going to be U0 plus U1 magnitude square. So I think that's what I have here. So you expand that. So you have U0. So it's U0 times A plus U0 plus U1 magnitude square. And that should be equal to this thing. So this will give me U0, magnitude of U0 square, magnitude of U1 square. These are these two first terms. And then the interesting part is U0, U1, U1 square. Let me say it again. U0, U1 conjugate multiplied with the U0 in front. And then U0 conjugate U1 multiplied with the U0 in front. We're just doing this magnitude square, right? You want me to write it down? So this is basically U0 square magnitude square plus U1 squared plus U0 U1 conjugate plus U0 conjugate U1. So this together gives you 2 times the real part of blah, blah, blah. This one gives you the cosine, right? But I want to keep it like this because now when I multiply with U0, I want you to see exactly what's going on. And what's going on is that I get these intensity terms. You see no phasing here because everything is magnitude. right? But at the bottom, the cross terms gives me U naught with the U naught inside, gives me U naught squared times U1, right? And the U naught squared times U1 conjugate, notice. So this is the forward, this is the backward. What this tells you is that if I take my hologram that I've written and I illuminate it with the same plane wave, I will get an exact replica of the field that made that hologram, one going forward and one going backward. Which means that if I go an exact distance away, like the distance where the hologram was written, the exact distance from where the hologram was from the object when I wrote it, what I'm going to get is an exact replica of the object at the exact same distance. Okay? So I take this, the written hologram, I illuminate with the plane wave, and if I look exactly at the distance where the hologram was sitting when I recorded it, I'm going to see a perfect object coming in, phase and amplitude. That's what impressed the people so much, because it looked 3D. It didn't look like an intensity image, it looked a phase and amplitude image, the way we see each other right now. So that made an impact of people. Oh, it looks 3D. Yes, it looks 3D. But again, the way our retina is 2D, clearly, except we have two eyes. That's the extent of our 3D imaging. We actually see in 2D pretty much, right? This slight depth perception is due to the two views of the same object, okay? Which is useful, again, don't get me wrong. That's the same reason we have 2 years to kind of be able to tell where things are kind of coming from. But let's face it, it's not the tomographic imaging. We don't have that. Okay. So, but this generated museums of holography. So they had little toys, little trains, terrible ladies, good-looking ladies. Back in the day, that was okay. They'll take a picture, and this will look 3D, and everybody will go visit. So every grandma understood what holography was, right? So it became kind of a commodity thing, as opposed to, I'm here to tell you that actually this is a very scientific subject, and actually the way you extract this phase and amplitude information has very deep physical meanings and important applications, okay? Besides the fact that they do look cool, your hologram on your credit card, even that looks cool. But there is actually scientific applications for that. Okay, so are we cool? Do we understand how these are formed? Because the transmission of my hologram is something to do with the intensity, which is magnitude square of DC plus AC. I expand this term, I multiply with the incident light U naught. I'm not sure why it looks so ugly. Okay. So when you do that, you get your field U1, which is this scatter part, the structure part, high frequency part, entirely, phase and amplitude. But the problem is, you also get the backwards one. So you know what this means? Can you think of a problem? There we go, much better. Can you think of a nuisance coming out of this? The fact that I have U1, so I have my beautiful, there's a famous little train that they used. I think the MIT Museum still has it. The hologram of a little toy train. And that would look in 3D when you looked at it. The problem is, on top of that image, you will get this image that is focused behind. So I'm looking at this screen. So I'm getting my beautiful image here. And then I have somehow another train behind. So the perfect image is here. If I focus here, I will get an out-of-focus version of that object that will be completely overlapped with the in-focus image that I'm looking at. These two are called, or this one is called ghost image. Just another way of putting names on stuff. But do you know where, can you think of where, if if you were to explain why do you get a pair of fields and not just one, using your Fourier knowledge that you are all experts on now, in the simplest possible way, how can you explain that you will get two replicas of the field and not just one? What's particular about this? This basically is my new object. The hologram itself, the piece of glass that has shades, right? Darks and bright on it, already written. That becomes a new object. What's particular about this transmission function? Look at it.
It's a shear, it's a shift, and
Well, it's real, right?
Real. It's real.
It's equal to transform.
It means when I put it here and I get the field propagating, right? The field starts to produce that Fourier transform, if we let it go far away. It has to give me two pairs. Always, if I start with the real thing, it has to give me two pairs, right? Cosine gives you two delta functions. Every cosine will give you two delta functions, right? If you have a real function, you will get a Hermitian Fourier transform. One Fourier transform and its conjugate. That's exactly what you see here. These two are Hermitian of each other. Huh? Yeah.
So when you say virtual image, like the electric field is actually...
I don't want to call it virtual. Did I call it virtual? I wanted
I mean,
to.
in the diagram it says virtual.
Is it virtual? Okay. They call it ghost images. Yeah. Okay.
So that electric field actually comes to my eye, or is it actually going backwards reflected? Because if you see, it has to come to my eye, right? It's not actually in that diagram. It's
So your question is, if it goes backwards, why does it bother me?
I mean, in actuality, there's no actual physical light going backwards, right? It's just, it's virtual because it looks like it's going backwards to my
Right.
Okay.
Yes. That's actually a very important point. So if the light here would be to propagate towards this way, it will never bother us. Right? So the light going that way, it will never reach my eye. But actually what happens is that the light is going towards me, except, okay, so let's call this virtual image, since this is the hologram plane, and then this is my actual image, real image. So I get my perfect image here. So all the light focuses to points, right? So this is one point on my train, this is another point. So these are perfectly in focus. Basically, this field is actually coming towards me, except it's out of focus. That's the reason we call it virtual image, actually. That in geometrical optics, you didn't take 460, but we call a virtual image the image that is formed by continuations of the waves, not where the rays actually meet. One example of that is when you look in the mirror in the morning, in your bathroom, your image appears to be formed in the wall. The exact same distance face to mirror, the image will be mirror in the back. So clearly that is a virtual image because there is no light going in the wall to make your image. So it's the exact same thing. So this light that is out of focus hits my observation plane, overlaps with the in-focus image. And that's what makes it annoying. The sad thing is, because of this little problem, Gabor gave up holography almost entirely by, I think, early 50s because of this ghost imaging. But that's when another method came about to fix this problem. So we call Gabor's holography inline holography, meaning you put a hologram on axis, you illuminate on axis, you read it on axis. It's all online, on the same line. You see what I mean? So off-axis is kind of different in the sense that now Basically, if I have, first of all, this was invented by these two people who worked at Michigan. Okay, there were some earlier papers actually on this, unfortunately in German. So they kind of share the credit for this. But Leith and Upatnieks are the two that are, their paper is mostly accredited with this. So the idea is that, here's the idea. If you, instead of illuminating inline, if you somehow bring your illumination at an angle, right? Or have the light hit your screen that goes through your object and then come up with the reference field at an angle. That simply offsets these two ghost images. They are not going to be overlapped anymore. They are going to be off axis. So if I look at one, here, my ghost image will be here. That would be ideal for me. I don't want my ghost image to send light on the same line. If I could offset it, so I look at this and I don't get this effect, that would be ideal, right? This is what off-axis holography does, and this is what saves the field of holography. Because the inline couldn't really kind of hit the wall at some point. All right, so imagine you have a plane wave hitting an object. I have my film here, so I'm writing the hologram right now. And now, notice, I have a separate plane wave that comes in, so it looks like this except it's at an angle, that also hits the film. And because of this angle, what do you think is going to happen?
You get a cosine.
You get the cosine, right? So you will have, so I'm writing the two fields together, so I have the reference, okay, this is the reference and this is the, there we go. I call this the Fresnel field, okay? So the film is in the Fresnel zone of the object, so a certain distance from the object, so I use a Fresnel propagator to there, our own formula here, convolution with the Fresnel kernel. And then on top of that, I have a reference that comes at an angle. So I'm writing basically the intensity, which is come on. All right, so the intensity will be, again, the magnitude square of the field. So it will be U Fresnel, which is the field of interest to me, and then a reference, UR, magnitude square. Okay? So this is going to be the intensity of one, intensity of the other one, this times that conjugate, and this conjugate times that. So the main difference with respect to the other equation that we wrote is that in that case, we had basically nothing off axis. Everything would be on axis. It's as if the U naught, the directed light, will serve as a reference. Different. And basically, mathematically, what we see is that we have this plane wave right here, which is this tilt. So you notice this is my kx. This plus this is going to give me a cosine on the film. This really comes out of the modulation theorem that we did in the Fourier transform, that I have my original signal, which is the same field as last time. But basically, by adding this reference at an angle, I'm imposing a cosine of the whole thing on top of everything else. So when you do the Fourier transform of that, it's going to split your image in two. That's it. So it's going to do exactly what we wanted. When I look at this, I'm not going to see this. They are not going to be in line anymore. This is going to split. That's what the cosine does. Splits your image in two. Okay? Simple enough, right? You may wonder why it took, I don't know, 8 years from 48 to the 50, 56, I think. to come up with this. All right. So this is the key, the fact that this is tilted at an angle. There is a phase change along x. This is this projection. And together with the conjugate one is going to give you a modulation on top of the whole thing. So basically, my resolution goes in and out. Because I'm not connected or what?
Yeah, you're not.
Oh man, is this normal?
Switch to Illinois then.
This one?
Yeah. You have to put in your net ID and password. You can use your keyboard.
Huh? I know I can use my keyboard.
I mean, you can disconnect it as well.
Okay. Okay, take a break, everybody. Oh, didn't work.
Did you change your password?
Yeah, with the Illinois net, it's kind of new to actually log on to that.
All right. Let's see how that transfers into better resolution. Might be looking better for you guys, right?
It's still readable.
Yeah. Do you see those pictures where if you look close you see Marilyn Monroe, if you look far away you see Einstein? Did you?
Yeah.
Okay, do you know how it works now based on what we learned here? High frequency and low frequency. So if you go far away from the image, you low pass filter the image, right? So you see whatever you decided to make your low pass figure. So basically you take two pictures, you make one low frequency, low pass it, keep the high frequencies in the other one, mix them together, and that's what you're going to see. You look up close, high frequency image pops up. You go far away. All right. So for me it's harder to read probably than for you. Isn't that funny? You are E2GIK not blah 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 blah. Okay, let's forget about that. You're going to read the equation by yourself. If I take now the recorded hologram, so the hologram was written by this beam and then a reference beam that came at an angle, right? So it has a cosine on top. Now, if I come in with the same reference, so now I'm reading step 2, I'm reading the hologram. Now the DC is going to be with respect to my incident light. Yeah? So the interesting thing is, it's going to give me one image right on axis where, you know, where the object was, right? So the object was on axis, I came off axis. All right, so now if I come off axis and I read that, it's going to give me my object back exactly where it used to be. And the virtual image is going to be shifted off axis here at twice this angle. There's a factor of 2 here. So basically this is problem solved. Because now I'm looking at this image and I see it, it's beautiful, and I don't get bothered by this. Yeah? The modulation theorem, or backwards, the shift theorem. That's it. Okay. Do you have any questions? Well, okay. We're going to do some nonlinear optics at the end, but basically, this was an interesting development in the early 70s that is actually resurfaced and re-energized in the past 8 to 10 years or so. And that is to do phase conjugation, so do some kind of holography with nonlinear crystals. So here's the idea. There are these crystals that have the property, because of their nonlinearity, they have the property that their refractive index changes as a function of intensity. So right there, that is a nonlinear system because, in other words, your transfer function or your impulse response of your system depends on your input, right? So completely the opposite of what we did with the linear systems. Meaning that if I put high power somewhere here, the refractive index will be higher or lower than where I have lower power somewhere else. So imagine for a second that I'm putting two beams into that crystal facing each other, for simplicity. How is the intensity going to look like if I put two beams like this?
Magnitude squared, right? So 4 times?
4 times and 0 times occasionally.
Oh.
There's interference.
Oh.
Hello? Right? I mean, it's the same problem as in microscopy, right? So you have the largest angles. If this is the objective, I collect all these angles. Gives me the finest sinusoid, right? That's the highest frequency from the object that I can collect. It's the same physics. When you put them facing each other, you get a sinusoid, right? The smallest, actually, because this is the largest component along this direction that I can make. If I put them at this angle, I will still get the sinusoid, but the wavelength will be, or the period will be larger. Are you guys with me or no? If I put two beams like this, it's going to give me, let's say, this sinusoid. If I put them like that, it's going to give me the finest possible sinusoid. But a sinusoid nevertheless. To the point where when I put them parallel, I get 0, infinite wavelength. Yeah? Okay, you need to put this together with all the microscopy resolution stuff that we discussed. It's the same physics. So imagine these two beams facing each other. They generate, basically generate a sinusoid like this. So what I meant is that at the peaks, when you put light plus light together, you get 4 times the intensity of each, but there are points where you get 0, right? Are we clear on that? Remember what my teacher said, that it's not so surprising that light plus light gives you more light. What's surprising is that light plus light gives you dark, can give you dark. Anyway, so this is the intensity. You have maxima and minima. The refractive index will follow this modulation, which means that this becomes a grating that only exists as long as I put this light on. Isn't that kind of cool? So this is one of the things you can do with nonlinear optics. So I'm turning light on, and then this crystal acts as a grating, which means if I shine this k vector in, a plane wave at any angle, basically, for this k vector sum to obey the conservation theorem, which is basically the momentum conservation, what comes out of this crystal, so sending k3 in, what comes out of the crystal has to be exactly k4, exactly minus k3. Okay, so let me say one more time. I apply two beams. If you apply then, and the crystal becomes a grating. If you apply a third beam at over any direction, that crystal is going to reflect perfectly back the opposite of what you put in. So it becomes kind of interesting that you can reverse. So this crystal has the ability to phase conjugate. This wave going outwards is the conjugate of the wave coming in. Hence the name phase conjugation. This technique was first invented and published in Russia by the teacher that told us that it's not surprising that light plus light gives you light. It's light plus light that gives you dark. That's surprising. So his name is Boris Zeldovich. And his paper was, I think, 1973 in Russia. A couple of years later, there are follow-up studies on this at Caltech by Professor Yariv. And then recently, the past 10 years or so, there's a kind of a re-energizing of this field. That people try to apply this to kind of reverse light scattering from deep tissue, so to be able to actually go deeper into the tissue. Okay, so you see how this is actually sometimes called dynamic holography, because this only exists as long as I have this, the two beams in the nonlinear optic crystal. Okay, so let's not spend any more time on the nonlinear part of it. I wanted to get to digital holography, but do you mind if we take a 5-minute bathroom break? Because it seems like I got the phone call from my daughter's school, so I want to make sure everything is okay. Okay? And I used to give, actually, I should turn it off. I used to give, actually, 5-minute breaks. Possibility. The fact that now you have image stored digitally and is ready, you can process it in MATLAB or any other program, gives us a lot of freedom. And basically, we see a great kind of effort that is now recently put into digital holography, especially for imaging. And this in part because of the advances in detectors and computing. And I'm going to now, for the rest of this lecture, I'm going to tell you a little bit about that. So, writing the hologram now takes place on, you can essentially image the whole thing instead of being at the Fresnel distance away. And this becomes a CCD camera where you get the information at each pixel. And one of the early applications of this, of digital holography, was to do kind of character recognition application. Okay? So what I mean by this is, do you know how this text recognition software kind of works? When you scan a paper and then it goes ahead and recognizes the text so you can actually search and whatever, import in a word. No? Even the scanner is obsolete. Well, on your cell phone, actually, you can do the same thing. OCR, come on. So the way it works is kind of like this. It's through correlations. So imagine I have a bunch of letters here. And, or you take a picture of a newspaper. And you want to recognize all the points where the letter A exists. So what can you do? Well, one way to do it, the most efficient way, is to take the letter A, which you know how it looks like, and correlate it with a picture with all the characters on it. And you look at the peak, exactly. Where you find the peak, this is, okay, it's right here. So the correlation is exactly the way we defined it. You take, do integral and so on with definition. Probably is even better if you do it in the Fourier domain. But at the end of the day, what you get is some kind of a pattern like this. And when A meets another A, you're going to get a very high peak. Meaning that correlation integral, the overlap is perfect. Therefore, when you do that integral, you're going to get the maximum value. Right? So you remember the correlation is about multiplying, which is the amount of overlap, and then integral of that overlap. So clearly, when you match, a character matches itself, you're going to have the highest overlap, precisely when they're at zero shift. So this tells you where the character A is. So then you do correlation with B, and you find all the B's, and so on and so on and so on. So now, the efficient way to do it is to take the Fourier transform of that, Fourier transform of this, multiply them, right? Multiply one with the complex conjugate of the other one, because the Fourier transform of a correlation is exactly that. And you get something like this. Okay, doesn't look very interesting, but the Fourier transform of that will give you automatically the correlation. So this is the fastest way to do this operation. Okay, so what is this to do with optics? Well, imagine now I have my transparency with a bunch of characters on it, and now I want to find the A's on this transparency. Okay, so I take the A, I take its Fourier transform, and I put that on the transparency. And then I take my object, I do a Fourier transform right at this plane with lens 1. So this is the Fourier transform of my object, of the unknown distribution of characters. But on top of it, I add the Fourier transform of the character that I'm looking for. You see what I mean? So essentially, I'm filtering the frequencies from the object, from the text. I'm filtering that with the Fourier transform of the character I'm looking for. So I just put that there. And then the second lens is going to do the Fourier transform back. And guess what I'm going to see? I'm going to see exactly this. Distribution of dots, where the dots are the brightest, is going to tell me where each of the character is there. So of course, this has other applications, like looking for, I don't know, little squares in your image, or looking for maybe nuclei in cell images. And this kind of optical processing, so what we're talking about, this is analog processing. The Fourier transforms take place at the speed of light. Okay? It's not MATLAB that's doing the processing. It's really the lenses that do the Fourier transforms for us. So this is one of the earlier applications. I've seen even recently people using this idea to find calcifications in breast tomograms or breast CT films. So you have a library of crystals or calcification images somewhere. Generate the Fourier transform of those, and then with a couple of lenses, you overlap the Fourier planes, and then you are going to get bright spots where all the calcifications are, which is kind of nice.
So normally when you just multiply two things in the Fourier domain, that's a convolution, right? And then if you want a correlation, you have to complex conjugate one of them.
Right.
And then, but you're not doing that. How are you getting a correlation?
No, I'm doing that. So one of them should be conjugated. And when you do it optically, the transparency, what you write on the transparency, you make it conjugated first. That's all.
Okay. But like, how would you physically do that? You would like put it on a mirror, or? You could do it with a computer, I imagine. But
So you're asking, how do I write this filter for the character A, let's say?
How would you get the complex conjugate
Of one of those.
of one of them? Yeah. Besides using a computer, could you like use a mirror and then shine it back, and would that work? Or
All you need to do is to flip it. So it's conjugated in X and Y.
like literally flip it upside down?
Yeah, 180 degrees. So the KX becomes minus KX, right? This K becomes minus K.
Oh, okay.
That's all. It's about, in convolution, one is flipped, one is not. Right? So in the Fourier domain, it just changes the signs of the K vectors.
And that works for the phase too?
For the phase, what do you mean for the phase?
The phase gets conjugated as well?
Yeah, so how do you do that without recording it?
I mean, it's not that important. It's like, if there is a physical way to do it, that they do.
No, I'm sure there is. I just never done it, so I never thought about it. But, No. Oh, I said it wrong. So, if this is my A character, whatever. So I'm making the filter for character A. This is my object. I'm using this lens. This is the Fourier domain. This is going to give me the Fourier transform of A, whatever. The way to get the conjugate is to flip the object. This will give you F conjugate of A. That's it.
Okay.
If you want to do convolution between this and the other object, wait. This should give you what we need, right?
Because think of a cosine, right? If you take a cosine, you get two deltas.
Yeah.
And then you get the complex conjugate of a delta.
Yeah, they are already. One is conjugated to the other, right?
Yeah. Or if you do a sine, you have one with negative, one
Right.
looking down, right? And so you want to flip those.
Right.
If you rotate it, if you rotate the grading, you still get 180 degrees. You still get the same thing. Or is that wrong? Yeah. So I think you have to use a mirror.
How would you use a mirror?
Like, doesn't a mirror phase conjugate? Maybe we're going too off, but.
I mean, yes, meaning that if I send my light this way, my light is going to go that way, right? But we're talking phase conjugating in this plane.
Like if you image the film and then.
Hold on. So this will be f of minus x minus y. And the Fourier transform of that, it will be f conjugate of kx, ky. Come on. So taking the Fourier transform of a flipped A, not rotated, it's symmetrically with respect to the origin. That will give you the conjugate, that's it. As simple as that. So then record this, put it in here, and you are going to get your dots where all the A's are. Okay? Is that okay? It's simple. Yeah? All right. Okay, so hold on, this is, to me, this is writing. Why is that saying reading? So that's not reading. Reading is this is writing. So we're writing on the camera now. So I have my transparency, my object. I project here, it could be the image of my object, or it could be any Fresnel distance, okay? Whatever it is, I want to use the phase and amplitude information. So for that, off-axis digital holography, the way it works is that you have your off-axis reference at an angle. And the main difference is that now the camera records your signal digitally, and you no longer need a physical film. What you record is the exact same thing. This is the exact same formula as before. Oh, notice the higher resolution, actually. So it's the same signal as before. Now you have the cosine on top. But now what do we do? So I have my image. It's a TIFF file on my computer. What do I do? How do I get my original file? My original field. I want to get the image of this. I want to get use MATLAB and propagate numerically according to, I think I have the Fresnel propagation right here. Or somewhere. This one. So imagine the magic. You record something that looks really like garbage. This is what your camera sees. So you notice there are some fringes here, but it really looks terrible. It's a completely out of focus image. But because you added that modulation, there is the phase information that is preserved. You take the Fourier transform, notice my flipped characters, okay? So basically the Fourier transform of this gives you the original input. In this case it was the letter P, okay? And I think the comparison is between the digital computation, and this is the actual photographic image of the object. So you see they're very, very close. Except in one case you started with the hologram that looks like this, looks nothing like your image. In the other case you just took an image of the thing. Okay, so once you have in digital holography, you remove all these kind of clunky physical films, photographic films for recording the image. You make a TIFF file and you process it numerically in your MATLAB or whatever program. So now you can actually generate, if you want, I can generate autofocus light. How this letter P will look like if I were to image it like, I don't know, 2 millimeters away. All that is now available because you have the file in a digital form. So this is, I think this paper is from here, from 67. Goodman, one of the leaders in our field of, if you want, optical information. He wrote a classical book on Fourier optics that is listed in your reference list. And his research was on these kind of things. And this is the first paper on digital holography. I mean, there are precursors to this where I think IBM used the printer, used the digital printer to write the hologram. So you see, that was kind of an intermediate step towards digital. So instead of using the film, they used the printer with dots. So remember one of those needle printers? So you make your holograms out of dots. Clearly, as opposed to glass, you cannot have your gratings kind of, how should I say? The phase information is not encoded perfectly. You encode it in the dots. And that being a real signal, that itself generates its own ghost images. But anyway, it was an important step towards getting to this one. So now we are 40 years, 50 years later, and this kind of scheme is actually used with the kind of new interests, especially in microscopy. So digital holographic microscopy is a thing, is a type of microscopy that's using that for looking at cells and tissues. So basically, these transitions into the field of what I call quantitative phase imaging, which is somewhat of a recent field that happens to be the subject of our research in my lab. And this is a field that's growing very fast because it's making use of this phase information that is difficult to measure. The difference with respect to how digital holography was invented is that we want to quantify the phase information. We don't want just to see images, to reconstruct those PE characters and whatever, but to actually map the phase shift at each point in a microscopic image. So we want to go a step further from what, for example, phase contrast microscopy did, where it was able to generate this high contrast image of a transparent cell. What we want now is to actually put numbers on that phase shift at each point in the field of view. And it turns out that has actually very interesting applications. Okay? So we are interested specifically in the image field, not a particular Fresnel random distance from the object. We want to be at the image plane where you get the perfect replica of the sample field, amplitude and phase. Except we're interested to recover that phase information. So in general, the image field UI, in 2D, you have amplitude that depends on X and Y, and then you can have both time dependence. So we are in time and space. So you can have a temporal dependence that oscillates at the mean frequency of the field. So for example, if you try to measure the phase of this white light, what's the meaning of that phase? You have this bunch of frequencies in there, right? What's the meaning of a phase shift that you could measure there? What was the meaning of Zernike's phase shift when we said we're going to put pi/2 phase in the path of a white light field? What did Zernike mean? He meant the average frequency. It turns out that there is a physical reason why that is. And he knew it back in the 30s. Actually, that filter that makes pi/2 or lambda/4 phase shift, path length shift, is associated with the mean frequency of the white light, which happens to be in green, around 550 nanometers. So, okay, so if you have many colors of light, the temporal oscillation goes as the mean temporal frequency. If you have many k vectors, which an image does, right? To make an image, you need a distribution of k vectors. Then the phase shift along one direction is actually the mean k vector along that direction. And then you have the phase information due to the object. Okay? So depending on where you operate, whether you modulate in time or in space, you can have a mixing between the image field and the reference. Okay? And there are two kinds of setups. One where you control the phase shift between the reference and the image in time domain. So I control this delay. So for example, I have a mirror that reflects off my reference beam, and I control that, those steps with very, very high accuracy, sub-wavelength. So I'm able to shift this, let's say, in increments of lambda over 4. Okay, so for this, it will be steps of 100-some nanometers. Or a second type of interferogram is when I create fringes in space. So off-axis interferometry is when the average K vector from the image is actually at an angle with respect to the reference. So in that case, I get my fringes spatially. I have to mix, in order to get to this phase, clearly, I cannot just put a detector here, as I told you many times, because the detector will remove this. You'll end up only with the intensity. The interference is the only way to actually get to that phase information. So I have to add a reference field, either inline, controlling the temporal shift, temporal delay between the two fields, or, and this is called phase shifting for clear reasons, or off-axis, where the K vector of the image, K vector of my reference are at an angle, and I generate spatial interferogram. There are pros and cons for both of them, and that's what I plan to tell you in the next 30 seconds. We're not going to finish this part. Okay. So imagine this is my sample. This is my imaging system, your microscope, could be. This is my image field. This is my detector. And now I come with a reference that, notice, is parallel to the mean K vector of the image. So it's on axis. This will be K image. This will be K reference, right? So they're parallel. But because somewhere here maybe I have a mirror or something like that, I can control this path length. Okay? So if I manage to do that, and I am able to increment the phase shift between the two by pi over 2, so I can get pi over 2 phase shift, pi, 3 pi over 2, and 0, or 2 pi. Then if you look at this equation here, imagine you make this 0, pi over 2, and so on. What happens is that you get cosine of phi. Then with pi over 2, you get sine of phi. With pi, you get minus cosine of phi. With the other one, the last one, 3 pi over 2, you get minus sine of pi, of phi. The idea is that you want to eliminate these unknowns. So this equation, from one intensity image, you have three unknowns. One, the power of the image, the intensity of the image, the intensity of the reference, and the phase difference between the two. So you have too many unknowns for one measurement. That's the reason, for example, phase contrast microscopy, Zernike's imaging, cannot give you the phase quantitatively, because it has all these in there. So by doing phase shifting, you are able to collect more data and essentially work this system of equations out. So you get rid of this, get rid of that, and then you extract phi quantitatively. Yeah? Okay. We'll finish this next time.